A small habitat sits between the grey moon and red Mars. The question is where humans could actually live once the word live has to survive pressure, rescue distance, and ordinary failure. Mars looks more like a world. The moon is close enough for Earth to stay part of the system. Neither fact answers the question by itself. So we will test the word carefully. First against the human body, then against the machines that have to replace a planet, then against the harder problem. What happens after the first fault, the first missed shipment, the first repair nobody planned? The answer changes as the standard rises. A place can be easier to reach and still be brutally hostile. That is the comparison, not romance, not a scoreboard. The real question is which failure chain humans can survive first. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Moon or Mars sounds like a choice between distance and romance. The familiar argument starts cleanly. The moon is nearby. Mars is a planet with a sky and weather. Its day is close to Earth's. Its surface is large enough to feel like a second world. From far away, those are persuasive facts. The trouble begins when we ask them to answer a question they were never built to answer. Distance and appearance are not the same thing as livability. Now look at how easily the old question misleads us. It rewards the facts we can see from far away. Diameter and color, distance and atmosphere, horizon. Those facts matter, but they do not show the repair chain. They do not show how many hours pass before a specialist can talk to the crew. They do not show how many months pass before hardware can arrive. They do not show how many assumptions break when the mission becomes routine rather than heroic. Let's place the same small failure on both worlds. A valve sticks, a seal begins to leak, the carbon dioxide reading creeps upward. Nothing dramatic has happened yet. The crew is alive. The system is not lost, but the base has just asked the only question that matters: how long until help can make a difference? We also need to separate ambition from evidence. Wanting Mars to be humanity's next home does not make Mars operationally ready. Wanting the moon to be a stepping stone does not make lunar living easy. The whole point of this comparison is to take the romance seriously enough to test it against failure. On the moon, Earth is not merely a distant home. Earth remains an operational partner. Radio support can be close to real time. Specialists can look at telemetry while the crew is still working the problem. A replacement part may not be instant, but the loop between discovery and response can be measured in human days, not planetary seasons. Think of the word live as a load-bearing beam. If we put too much vague meaning on it, it bends. It starts to mean visit, then survive, then something larger than survival. Then every argument can claim victory. A careful documentary has to unload the beam and ask which meaning is being used at each step. Mars changes that contract. Earth can still listen. Mission control can still advise. But every voice arrives late, and every physical response arrives later still. The same small failure sits inside a longer chain. The problem is no longer just the leak or the valve. Even the filter is now part of a larger danger. The deeper problem is the distance wrapped around it. The phrase failure chain gives us a better tool. A failure chain is the path from small fault to serious consequence. It begins with detection, then comes diagnosis, then isolation. After that, the question widens into spare parts, crew skill, and power margin. Medicine and communication sit in the same chain. So does the possibility of leaving. The shorter and more repairable the chain, the easier it is to call the place livable under early definitions. And that is why Moon versus Mars is the wrong first question. The better question is not which place inspires us more, The better question is which place lets a fragile human system fail, recover, and learn. Then it asks something harder. Can the system fail again without each mistake becoming final? And this is why the Moon keeps returning to the argument, even when Mars has the better planetary story. The Moon lets Earth remain part of the chain. Mars forces the chain to close locally. A settlement may eventually need that closure, but the first attempts at living will probably need the opposite: room to be wrong. We need the word live to do careful work. If it means walking outside without protection, both worlds fail at once. If it means surviving inside a sealed machine for a mission, the answer changes. If it means returning again and again with infrastructure that improves, the answer changes again. If it means a true settlement, where human life continues after rescue is no longer the default, the word becomes heavier. So we are not choosing a favorite world. We are building a scale. At the bottom is raw biology. At the top is a society that can absorb damage. Between them sit machines and logistics. Maintenance comes next, so does human endurance. The Moon and Mars occupy different positions on that scale depending on which rung we are testing. The Moon has a harsh surface and almost no natural help. Mars has more planetary ingredients and a much harsher recovery problem. Those two truths pull against each other for the whole documentary. Neither one disappears because the other sounds more convenient, so here is the frame we will keep returning to. The most livable world may not be the one that looks most like Earth. It may be the one where Earth can still keep the failure chain from running all the way to the end. That does not make the Moon safe. It does not make Mars impossible. It makes the comparison honest. And once the question becomes honest, the first answer arrives quickly. If living means the body can survive the place itself, the Moon and Mars both fail before the argument has really begun, so the comparison keeps moving back to recoverability. Wonder is still allowed here. It just has to survive the bill that comes after arrival. A world beyond Earth becomes more interesting when we ask what it takes to keep people alive there after the first triumphant image fades. So we need a method that refuses the postcard version of the question. We start with the body. Can the world itself keep a person alive? Then we move to the machine. Can humans build a survivable pocket on the surface? After that comes repeatability. Can people return often enough that presence becomes normal rather than heroic? Only then do we ask the hardest question. Can the system absorb ordinary failure without Earth immediately becoming the missing organ? Those 4 tests matter because they stop one fact from pretending to be the whole answer. Mars has the stronger planet-like story. The Moon has the stronger reachability story. A serious answer has to let each advantage win only where it actually wins. This also protects us from a common trap in space arguments, treating firsts as futures. The first landing can be historically enormous, so can the first habitat. An oxygen experiment or rover track may matter too, but none of them proves by itself that people can live there. Firsts prove access. Living proves endurance, so when we compare Moon and Mars, we should not imagine a scoreboard with one column for romance and one column for engineering. We should imagine a crew and a base, then imagine the broken part. Only after that should we add the supply chain and the clock. The clock is different on each world. That difference will keep returning. On the Moon, failure can remain connected to Earth. On Mars, failure becomes more local, more delayed, and more consequential. That does not make Mars the wrong dream. It makes Mars a later and harder definition of the same dream. We are going to keep that distinction alive. The Moon may be the better place to learn how to live beyond Earth. Mars may be the better place to ask whether humans can one day live more independently from Earth. Those are not the same claim. The first wrong answer is to treat closeness as safety. Closeness helps only when the rest of the system can use it. A lunar habitat still needs launch readiness and landing precision. It needs compatible hardware and a healthy crew. Most of all, it needs enough time for any response to matter, so the Moon's advantage is conditional, not automatic. The second wrong answer is to treat Mars's planet-like qualities as destiny. Mars has a day and a horizon. It has weather too. Beyond that sits a richer resource canvas. But those features become livability only after they are connected to working infrastructure. A sky does not repair an oxygen valve. A planet does not automatically become a support system. So the comparison has to stay disciplined. The Moon's case is not that it is easy. Mars's case is not that it is already home. The Moon's case is that early mistakes can be corrected through a shorter loop. Mars's case is that a mature system there would mean a deeper kind of off-world capability. We need both ideas, but in the right order. One more discipline helps here. We should ask what a place teaches first. The Moon teaches recoverable failure because Earth can remain near enough to close the loop. Mars teaches autonomy because Earth is too far away to act like a normal support team. A mature spacefaring civilization may need both lessons, but a first lesson and a final exam should not be confused. So the opening test remains practical rather than poetic. A fact only helps the Moon or Mars answer when it changes the crew's ability to recover or continue. The deeper test is whether it makes the crew less dependent on rescue. Everything else may be important background, but it cannot carry the word live by itself. That is why the frame is deliberately severe. A world earns liveability by protecting recovery, not by winning a mood board. So the comparison keeps returning to the clock, because the clock decides whether a mistake becomes data or disaster. The body is the first judge, and the body is not romantic. Natural habitability means the world itself is doing enough work to keep a person alive. Earth does this so completely that we stop noticing it. Air presses on the body from every direction. Oxygen arrives with every breath. Liquid water can remain liquid in ordinary places. Temperature stays within survivable ranges across large parts of the surface. Radiation is filtered before it reaches us at full force. Now the reason this first definition matters is that it prevents a very common slide. People see Mars's clouds and valleys. They see polar caps and a day-night rhythm. The mind quietly upgrades it from hostile world to harsh frontier. That is understandable. It is also wrong in the one way that matters most to lungs and blood. Now take those gifts away one by one. The question stops being philosophical. It becomes physical. Can blood stay pressurized? Can lungs move gases across a membrane? Can skin, eyes, and tissue tolerate the outside environment? Can the body do anything useful before the place overwhelms it? The Moon makes fewer promises. Its black sky and bare surface warn us immediately that we are outside Earth's biological bargain. Mars is more dangerous to imagination because it gives familiar cues without the underlying support. A sky is not enough. Ground is not enough. A day is not enough. The body needs a whole stack of conditions delivered together. The Moon gives a clean answer. It has no breathable atmosphere. Its surface is exposed to vacuum and radiation. Micrometeorites add another hazard. Extreme temperature swings make the outside even less like a place biology can negotiate. A person outside a suit is not in an extreme desert. We are outside the category of landscape that biology can negotiate. The body needs a pressure vessel before any other discussion can begin. Let's define the body test as simply as possible. A naturally habitable place lets a person exist for more than a moment without carrying their atmosphere. That means breathable chemistry and adequate pressure. It means tolerable temperature and radiation protection. It also means water behaving in ways biology can use. Neither the Moon nor Mars comes close to that complete package. Mars is more deceptive. It has a sky and weather. It has seasons. A day on Mars is close enough to an Earth day that our intuition begins to relax. But Mars's atmosphere is mostly carbon dioxide and the pressure is far below what an unprotected human body can use. The planet looks more familiar than the Moon, but it does not give the body what the body needs. This does not make the comparison pointless. It clears the ground. Once both worlds fail natural habitability, every serious answer becomes an engineering answer. We stop asking which planet is nice enough and start asking which constructed system can keep the outside from becoming the inside. So the first definition removes the easy fantasy. Neither world is naturally habitable. Mars is not almost Earth. The Moon is not merely a nearby desert. Both are places where the first requirement for life is an artificial boundary between the human body and the world. And that shift matters for viewer satisfaction because it breaks the shallow debate. Mars may feel like the candidate for living because it is a planet. The Moon may feel like a campsite because it is nearby. But if the first act of living is sealing yourself from both, then the seal and its support chain become the real subject. That boundary matters because every later claim has to pass through it. A habitat is not a building in the ordinary sense. It is an atmosphere machine. A suit is not clothing. It is a personal spacecraft. A base is not a village. It is a controlled environment pretending for a while to be a planet. So the first definition gives us a hard floor. Below it there is no winner. Above it the argument becomes more interesting because engineering can compensate for natural failure. The rest of the documentary lives above that floor. Let's be careful with the comparison here. Mars has more natural features that feel useful. The Moon has almost none. But natural habitability is not a feeling. It is pressure and chemistry. It is temperature, shielding, and water in forms the body can use. On that test, both worlds stop us at the door. The useful lesson is not that one world is worse. The useful lesson is that the word live cannot begin with the landscape. It has to begin with the machine that replaces the landscape. And once the machine enters the question, proximity starts to matter in a way appearance cannot. A sealed habitat on the Moon and a sealed habitat on Mars may look similar from inside, but the systems supporting them belong to very different worlds. So the body test gives us the first clean answer: neither. The next definition asks whether engineering can build a small Earth where the planet refuses to provide one. And we should hear the humility in that. The evidence rejects the easy story without pretending the frontier has disappeared. Good science does not make the problem smaller. It shows us where the real edge begins. The natural habitability test is deliberately unforgiving. It does not ask whether a place has useful ingredients. It asks whether the place itself does enough continuous work that a human body can function without a sealed artificial environment. On Earth, that work is so complete that we barely have language for it. Air pressure is just there. Radiation protection is just there. The water cycle and nitrogen cycle do part of the work. Weather and oceans do more. Soil and biology complete a planetary support system older than human planning. The Moon and Mars remove that inheritance. The Moon removes it obviously. Mars removes it deceptively. Mars has landscapes that can resemble deserts and riverbeds. It has cliffs, ice and weather maps, but the resemblance does not cross the membrane into the body. A person cannot breathe the Martian atmosphere. A person cannot use the pressure. A person cannot treat the outside as a place where biology has ordinary rights. This is why the first answer has to be neither, even if that feels unsatisfying. Neither world offers a natural human habitat. Both make the human body dependent on pressure vessels and suits. Air processing and temperature control matter from the first minute. Radiation strategy does too. But the failure of this first definition is useful. It tells us that any honest Moon or Mars answer must be an answer about engineered environments. The comparison is not between two homes, it is between two places where humans may build small controlled islands of Earth, then try to keep those islands from shrinking. That may sound severe, but it clarifies the wonder. The achievement would not be that humans found another Earth nearby. The achievement would be that humans learned to preserve Earth-like conditions where the universe does not provide them. This first definition also keeps us from smuggling Earth into the picture. When people imagine living somewhere, they often imagine buildings and vehicles. They imagine food, schedules, and community, but all of those sit on top of the invisible permission Earth gives the body. Take away pressure and air, and the most sophisticated city becomes unreachable without a suit. On the moon, the lack of natural habitability is so obvious that it can almost be clarifying. No one should mistake the lunar surface for a rugged Earth environment. Mars is more subtle. It invites frontier language because it resembles a cold desert through a camera. But a cold desert on Earth still has pressure and breathable air. Mars does not, so we start with a hard reset. Any human life on either world begins as indoor life in the deepest sense. The outside is not a normal outside. It is an environment that must be filtered through machinery before it can touch the body. That fact should follow us through every later claim, so the first definition strips away destination branding. The moon is not livable because it is close. Mars is not livable because it looks planetary. Both become livable only when a human-made environment interrupts the natural environment completely enough for biology to continue. That interruption is the beginning of every real off-world story, so the body test ends with a narrow gate. The question is not which landscape looks more plausible to a camera. The question is which world gives biology enough help before machinery intervenes. On that first gate, neither world passes, and every later answer must admit it. The first definition is therefore a boundary line, and crossing it requires machinery before preference enters the room. That boundary is why every later advantage has to pass through a sealed habitat before it can help. The first real off-world home is not a home. It is a machine that must not stop. We have established that neither the moon nor Mars keeps the body alive naturally. The question that remains is whether humans can build a controlled pocket of Earth and keep it working long enough to matter. That is engineered survivability. It is the first definition where off-world living becomes possible at all. Now think about how many planetary functions the habitat must imitate without calling attention to itself. It must make pressure feel boring. It must make oxygen feel ordinary. Waste has to disappear into a loop. Danger has to become routine through sensors and procedures with redundancy underneath. The better it works, the less alive the machine seems. Picture the habitat from the inside. The floor is not important because it looks like a room. It matters because pressure holds above it. The walls are not important because they divide indoors from outdoors. They matter because every square meter is resisting a place that cannot be breathed. The quiet hum in the background is not ambience. It is life support doing the work of a planet. That invisibility is risky for storytelling. Viewers can imagine a dome, a module, or a tunnel. Fewer people imagine the maintenance logs that keep the dome habitable. A base is only a home, while a chain of devices continues to behave within tight limits. Outside those limits, it becomes a container in a hostile place. Now the comparison changes. The Moon and Mars both require pressure and oxygen. Carbon dioxide removal is just as basic. Behind that sit thermal control and water recovery. Power has to hold them together. Medical support and contamination control come after, with a way to leave in reserve. But the ear cannot hold that as a list, so let's reduce it to the core. The habitat must keep air safe. It must keep temperature survivable. It must keep failure from spreading faster than the crew can respond. On the Moon, that chain can lean outward toward Earth. Early crews do not need to pretend they are independent pioneers. They can be operators of an Earth-supported system placed on another world. That is still extraordinary, but it is a more honest claim than calling the Moon a self-sufficient home. On the Moon, the machine can be fragile in a way that still leaves room to learn. Earth can help diagnose. Earth can send upgraded parts. Crews can rotate more easily. A design flaw discovered early can feed into the next mission while the lesson is still fresh. The Moon lets us be beginners closer to home. Mars is more demanding because Earth support cannot arrive inside the same practical window. The base must carry more knowledge inside itself. That means spares and training. It means local diagnosis, repair capability, and procedures that still work when Earth cannot shape the first decision. Mars gives less forgiveness. A habitat there cannot depend on rescue as a near-term layer of the system. It must carry more spares and more autonomy. Medical independence has to be deeper. So does the capacity to improvise from local materials. The same engineering task becomes less about building a sealed room and more about building a sealed room that can survive long periods of being on its own. Let's not oversell the moon either. A close, fragile bubble is still fragile. A lunar habitat can lose pressure or power. Cooling can fail. Air quality can drift. Rescue may be possible in principle and impossible in a specific moment. The moon's advantage is not safety. It is the possibility of faster correction. Here's the important distinction. Engineered survivability does not mean independence. A submarine survives underwater, but it is not an ocean settlement. The International Space Station survives in orbit, but it depends on regular logistics. A lunar base could survive in the same basic sense. Intensely engineered, dependent, monitored and resupplied. That can still count as living under one definition, but only under that definition, and faster correction is what early living really needs. First systems will not be perfect. They will reveal mistakes. The question is whether those mistakes can become design improvements before they become endings. In that narrow but crucial sense, the moon behaves like a more forgiving engineering classroom. Mars makes that definition more expensive because dependency becomes harder to maintain. Every kilogram of spare capacity must be launched and landed. Then it has to be stored, protected, and found when needed. Every procedure must assume that the expert on Earth cannot simply talk the crew through a live emergency in normal time. Every medical decision carries more weight because evacuation is no longer a nearby option. So we should not ask whether a habitat can exist on the moon or Mars. It can, at least in principle, if the engineering is good enough and the mission is short enough. The sharper question is how much outside support the habitat needs before we are willing to call the place livable, and we should not confuse the crew's courage with the place's livability. Humans can survive in brutal conditions for a mission. That does not mean the environment supports human life. It means the machine has won for that duration. The next step is the one that decides early strategy. The machine can work for a while, but the test that separates the moon from Mars is what happens when the machine needs help. So the question keeps narrowing. Dust is not scenery. It is a contact problem between a hostile surface and every machine that has to open and seal. The same machine may also have to turn, pump, and breathe. Engineered survivability is where the question becomes possible, but also where language becomes slippery. A habitat can keep people alive and still be nothing like a home. A mission can survive 6 months and still tell us little about 10 years. A base can be impressive and still depend on Earth for the parts that make it look independent. So we should grade the machine by its failure behavior. How many independent ways can it keep pressure? How quickly can it isolate a leak? How much carbon dioxide removal capacity exists after one unit fails? How long can it hold thermal control if power is reduced? How much can the crew repair in suits with gloved hands and limited tools? And how much does fatigue change the answer? On the moon, early engineered survivability can be more honest about dependence. A lunar habitat does not need to pretend that Earth has disappeared. Earth can remain the deep workshop and the medical backstop. It can also remain the design office and training base. The logistics reservoir stays close as well. That is not weakness if the goal is learning. Mars changes the threshold. A Mars habitat has to be less dependent, not because independence is romantic, but because the geometry of the solar system forces it. The crew must carry more capability inside the mission before the hatch ever opens. That means the first Mars base may need to be more mature than the first lunar base, even if both are only trying to survive. This is the quiet advantage of the moon. It allows engineered survivability to develop by iteration, build and operate, damage and repair, redesign and return. Mars compresses more of that learning into the pre-launch design because the post-failure loop is too long. So if engineered survival is our definition of live, the Moon takes the early lead. It is not because the surface is easier, it is because the total system includes Earth more effectively. The more engineered the living space becomes, the more design philosophy matters. Do we build systems that are highly efficient but difficult to repair? Do we build rugged systems that waste mass but survive rough handling? Do we standardize parts across air and water systems? Do power and mobility use the same repair logic so a crew can improvise? These choices are not cosmetic. They shape whether a base can survive its first serious maintenance season. The Moon lets those choices be tested with a more forgiving development rhythm. A flawed component can be studied, replaced and redesigned while the whole program remains close to Earth. The learning does not have to be perfect on the first attempt. Mars pushes against that comfort. The first deployed systems need a higher level of completeness because the next chance to correct them is so far away. That raises the cost of confidence. It is not enough for a Mars habitat to work in a test chamber. It has to work while cut off from fast rescue. It has to work under dust and delay. Partial gravity adds uncertainty. The psychological load of distance sits over all of it. So engineered survivability is possible on both worlds, but the margin for immaturity is different. That difference is one of the strongest reasons the Moon belongs earlier in the sequence. This is why redundancy has to be practical, not decorative. A backup that cannot be reached or powered is not a real backup. If it cannot be diagnosed and repaired under stress, it is only a comforting idea. On the Moon, weak redundancy can be exposed and improved through faster cycles. On Mars, weak redundancy may not reveal itself until the crew is already committed to living with it, so the machinery test has to judge more than first operation. A life support system that works only while new is a mission asset, not a living foundation. The Moon helps early because failed machinery can become a lesson quickly. Mars asks the lesson to be learned before the failure matters. The engineered bubble must be judged by its second bad day, because the first bad day only reveals the weakness. In practice, the best machine is the one that lets imperfect people recover without perfect conditions. Distance is not just travel time. It is the shape of every emergency. A pressure warning on the Moon is not gentle. A pressure warning on Mars is not automatically fatal. But they live inside different clocks. That is the rescue distance test. It asks how quickly information and people can move once a problem begins. Then it asks whether hardware and replacement options can move fast enough to matter. Now consider medical risk. A crew member develops abdominal pain, or a dental infection, or an injury during an exterior operation. On Earth, a hospital is part of the environment we assume. On the Moon, a hospital is far away but not absurdly beyond reach. On Mars, medical care must be far more complete inside the mission from the beginning. Let's use the same failure again. The habitat pressure is dropping slowly. The crew isolates habitat zones. They check seals. They look for a sensor error. On the Moon, the conversation with Earth can still feel like a conversation. Mission control may not save the crew by talking, but it can participate in diagnosis while the situation is unfolding. The same applies to software. A fault in control logic, a bad sensor reading, a confusing alarm cascade. These are not science fiction problems. They are normal problems in complex machines. Lunar support can be interactive. Mars support becomes delayed guidance that forces more authority into the crew and the onboard systems. Now put that failure on Mars. A message leaves the habitat and takes minutes to reach Earth. The reply takes minutes to come back. At certain distances, the delay can approach tens of minutes one way. That turns every exchange into correspondence. By the time a suggestion returns, the crew may already have tried 3 other things, or moved into a different failure state. So when NASA frames Mars-class missions as involving years away from Earth, the number is not just calendar time. It is a description of how long the crew has to live inside its own consequences. The Moon's days-long distance allows a different risk posture. Mars's months and years force a different civilization posture, and delay is only the beginning. The Moon can be reached in days. Mars missions are built around months of travel and launch windows that open on planetary rhythms. A missing component on the Moon can become a logistical scramble. A missing component on Mars can become a design philosophy. If it was not already there, the crew may have to live without it. Let's also remember launch windows. The Moon is not always easy, but it is frequently reachable compared with Mars. Mars launch opportunities depend on orbital geometry, with favorable windows roughly every 26 months. That rhythm changes planning from response to pre-positioning. You cannot send the thing you forgot when you remember it next week. So the Moon's advantage is not kindness. The lunar surface is harsh, the dust is abrasive, the radiation environment is serious. The temperature cycle can punish machinery, but the Moon allows Earth to remain part of the emergency architecture. Earth can still be in the room, at least operationally. Here the Moon has its most practical argument. It can teach through iteration. A flawed gasket or a dust-tolerant hinge can teach quickly. So can a better suit bearing or a revised medical kit. These lessons can move through missions on shorter cycles. Mars demands more of the first deployed version because the correction loop is longer. Mars requires a different kind of crew and a different kind of base. The people there must be operators and repairers. They must be medics too. Under delay they also become improvisers and decision makers. The habitat must assume that external help is slow enough to be background, not response. The architecture has to absorb more mistakes locally, and that is why rescue distance belongs early in the answer. It is not one category among many. It changes every category that follows. Here is where the familiar comparison reverses. Mars looks more like a place. The Moon behaves more like a reachable work site. If living means early engineered survival, reachability can matter more than scenery. A place close enough to rescue may be more livable in practice than a place with a more natural-looking sky, but we need to keep the claim narrow. Lunar rescue is not easy. A launch may not be ready. A landing site may be difficult. A medical evacuation may still be dangerous. The point is not that help is guaranteed. The point is that help remains inside a timescale where plans can still use it. On Mars, the safety case changes from rescue to endurance. It asks what happens if the crew must remain healthy, organized, and technically capable through the failure rather than away from it. That is a much more demanding definition of living. Distance does not only change travel, it changes the meaning of every hazard. And one of the hazards it changes most quietly is radiation. That is the operational discipline this question needs. We judge each system by how it fails and who can repair it. Then we ask how much time the crew has before one broken part becomes several broken assumptions. The rescue distance test also changes how honest we can be about risk. On Earth, we build high-risk work around layers of response. Offshore platforms and submarines accept danger. Antarctic stations and high-altitude expeditions do too, but they still build around evacuation and communication. Spare capacity and specialist intervention remain part of the safety logic. The Moon and Mars inherit that logic differently. A lunar crew may still be in grave danger during a serious failure, but a lunar mission can imagine response as part of the architecture. It can imagine urgent diagnosis from Earth and faster redesign cycles. Emergency cargo may be possible in some scenarios. Eventual evacuation can still belong to a timescale humans can plan around. Mars forces a deeper change. If the crew needs a part that is not present, the answer may not be shipment. It may be substitution or repair. It may mean cannibalizing another system, or it may mean accepting reduced capability. If a medical condition worsens, the answer may not be evacuation. It may be treatment with what is already there. If a disagreement arises during an emergency, mission control cannot smooth it in real time. That is why distance is not just a number in kilometers. It is a force that reshapes authority. Near Earth, mission control can remain a live partner. Far from Earth, the crew becomes more sovereign because reality gives them no alternative. This sovereignty is both inspiring and dangerous. It is inspiring because it is the beginning of genuine off-world autonomy. It is dangerous because autonomy earned by distance arrives before the systems may be fully ready. So the Moon is better for early recoverable living. Mars is better for testing the harder version later. Can a human group remain competent when Earth can advise, but cannot immediately intervene? The rescue distance test also shapes public expectations. Viewers often hear that the Moon is only a few days away and imagine a simple rescue. That is too easy. A rescue mission would still require hardware and timing. It would need trained people and the right trajectory. Landing would still have to work. So would surface operations and safe return. The Moon is close compared with Mars, not close compared with a hospital. But comparison is the point. A lunar emergency can still be planned inside a world where help may arrive, advice may be live, and evacuation may be possible. Mars emergencies are designed around the assumption that the first answer must already be on Mars. That changes the crew's relationship to risk. A lunar crew can take certain risks knowing that the wider Earth system remains near enough to matter. A Mars crew has to carry more of the wider system inside itself. It needs spare capability, not just spare parts. It needs authority, not just instructions. It needs medical judgment, not just a medical kit. So distance turns into maturity. The farther world demands a more adult system before humans arrive. The clock also shapes courage. A crew may accept risk differently when a rescue path exists, even if it is difficult. Without that path, the same risk becomes heavier because it must be absorbed locally. That is not a moral difference between worlds. It is an architectural difference created by distance. So the distance test converts place into time. Close means advice can shape events while they are still unfolding. Far means the crew must absorb more of the event before Earth can respond. That timing difference is one of the cleanest separators between the two worlds. Distance decides whether help is part of the emergency or part of the aftermath, and that distinction changes everything. This is the hidden geography of the debate, not terrain, but response time and consequence. Radiation is weather the body cannot see, and Earth normally takes the impact for us. We often imagine weather as something with clouds, dust, or rain. Radiation is different. It crosses space without looking like weather at all. Galactic cosmic rays and solar particle events do not need a storm front the eye can follow. They arrive as particles and energy, and the body has no sense organs that says the exposure is rising. Now the numbers are useful only if we hear what they mean. A millisievert is a unit of radiation dose equivalent, a way to express biological risk from exposure. The Moon's measured surface rate and Mars's measured surface rate are not everyday numbers for most listeners. What matters is the comparison to Earth. Both worlds remove the shielding we take for granted. Earth hides this problem beautifully. The atmosphere provides mass above us. The magnetic field changes the path of many charged particles. We still live with radiation, but not with the same raw environment found beyond Earth's protection. Once we move to the Moon or Mars, shielding becomes part of the definition of livability. Let's walk the arithmetic in plain terms. If a lunar surface rate is about 1.37 millisieverts per day, then 30 days exposed at that rate is roughly 41 millisieverts before mission details change the estimate. If a Mars surface rate is about 0.64 millisieverts per day, 30 days is about 19 millisieverts. The exact health meaning depends on many variables, but the exposure is not trivial. The Moon has almost no natural answer. Measurements from the lunar surface have reported dose rates around 1.37 millisieverts per day. The exact operational risk depends on timing and solar activity. Shielding and duration matter too. But the headline is clear enough. The exposed lunar surface is not a place for casual long-term human presence, and then Mars adds the crews. Measurements during the Mars Science Laboratory cruise reported a higher dose equivalent rate than on the surface. That means Mars's surface advantage cannot be separated from the journey that gets people there. Living on Mars includes traveling through the radiation environment between worlds. Mars gives a partial natural answer. Its thin atmosphere does reduce some exposure at the surface. Curiosity's radiation instrument measured average surface dose equivalent rates around 0.64 millisieverts per day, with higher rates during cruise to Mars, around 1.84 millisieverts per day in the cited measurements. Mars is not safe. It is less bare than the Moon in one important way. The engineering response is mass. Put enough material between the body and the particles, regolith and water become part of the architecture. So do structure, storm shelters and underground spaces. A window with a view is not the natural center of long-term living. The safe center may be the most protected part of the base. So a shallow scoreboard would give radiation to Mars, but the comparison is not that simple. To live on Mars, the journey matters. Months in deep space are part of the life story, not a preface we can ignore. The transit exposure and the surface exposure belong together. Return exposure adds more. Weaker rescue options sit in the same risk chain. The Moon's lack of atmosphere makes shielding more urgent at the surface. Mars's atmosphere buys partial help, but not enough to relax. In both cases, radiation pushes living inward. It makes the outside a place for work and exploration. Exposure has to be carefully timed, not casual permanent presence. On the Moon, surface radiation can be harsher, but the operational loop is shorter. Shielding strategies can be tested and repaired close to Earth. They can be upgraded and inspected on shorter cycles. A storm shelter can be improved between missions. Regolith can be studied as shielding mass. Mistakes are still dangerous, but the learning cycle is less punishing. So radiation gives Mars a real surface advantage and the Moon a real operational counterweight. One world has more natural shielding, the other has a shorter path back to Earth-supported learning. That is the pattern again: planetary ingredients versus failure recovery. On Mars, the atmosphere helps. That matters, but it does not replace Earth's atmosphere. It does not remove the need for mass, burial and shielding. Forecasting and monitoring remain part of the system. Operational discipline does too. A Mars base still has to ask where people sleep, where they shelter during solar events, and how much cumulative exposure a crew can accept. Let's translate the lesson. Radiation does not decide Moon or Mars by itself. It changes what kind of living is plausible. Exposed surface living is not the right picture for either world. Serious habitation begins to look buried, shielded, or tucked behind enough mass that the outside is no longer allowed to touch the body freely, and that changes the psychology of the place. The landscape may be beautiful, but the safe world is inside the wall. The sky may be black or orange, but the livable environment is the one we build away from the sky's full exposure. A planet-like sky helps. It does not replace Earth. And once we accept that the outside must be managed, the ground itself becomes another part of the machine, and the honest answer is not confidence, it is a boundary. We know enough to reject simple claims about partial gravity being harmless. We do not yet know enough to treat either world as a proven place for generations. Radiation also forces us to separate visible landscape from livable volume. A camera may love the surface, a human body may need to spend much of its safest time behind shielding or under regolith. It may be inside a protected core, close to a storm shelter. The livable world is not necessarily the scenic world. On the Moon, that point is stark. With almost no atmosphere and no global magnetic shield, the surface is exposed. Solar particle events become operational concerns. Galactic cosmic rays become part of cumulative mission risk. The base has to carry or use mass intelligently, because mass is what turns exposure into something more manageable. Mars has a partial atmospheric shield, and that matters. It gives Mars a real advantage over the Moon for surface exposure. But partial help should not be mistaken for Earth-like protection. The atmosphere is thin. The journey to Mars adds exposure. Long stays add exposure. The safe architecture still needs protected sleeping areas and storm shelters. It still needs monitoring and mission rules that respect cumulative dose. This is where Mars's planetary character helps without solving the problem. The thin atmosphere is an ingredient. It is not a completed safety system. The Moon's lack of atmosphere hurts, but its proximity allows shielding approaches to be tested, upgraded and replaced on shorter cycles. We should also remember that radiation risk is probabilistic, not theatrical. It may not look like immediate disaster. It may look like elevated lifetime risk and operational limits. Mission planning constraints follow. So does medical uncertainty. That makes it easier to ignore in a dramatic story and harder to ignore in a serious settlement plan. So radiation gives Mars a meaningful point on the surface, while keeping the broader answer open. The safer place to stand is not automatically the easier place to live, because living also includes getting there, staying supplied and recovering from the next problem. Radiation also affects architecture in a way that changes the image of settlement. A surface base with broad windows may look appealing. Long-term safety may push people toward buried modules, covered corridors and regolith-protected rooms. The place where humans actually live may be less photogenic than the place they explore. On the Moon, this may mean using local regolith as shielding mass sooner rather than later. It may mean designing habitats to be covered, not simply landed. It may mean treating storm shelters as central spaces rather than emergency closets. On Mars, the atmosphere may reduce the burden, but the journey and duration keep the problem alive. A Mars settlement story has to count transit dose and surface dose. Solar events matter too. So does the effect of repeated missions over careers. It cannot treat radiation as a one-time obstacle cleared by arrival, so radiation gives us another definition test. A short visit can accept exposure budgets that a settlement cannot. Repeatable life needs architecture that makes safety ordinary rather than heroic. Radiation therefore belongs in the same category as pressure and power. It is not background, it is one of the conditions the base must continuously negotiate. The Moon asks us to solve it with almost no atmospheric help. Mars gives partial help, then asks us to solve the transit and duration problem as part of the same life story. So radiation has to be treated as a design pressure. Mars gains something real from its atmosphere, but not enough to make exposure ordinary. The Moon loses that atmospheric help, but gains a faster learning loop for shielding that must become part of normal architecture. Radiation makes safe volume precious, pushing serious habitation toward protected cores instead of exposed frontier imagery. The safer shelter may be less cinematic, but livability has never promised to be cinematic. Dust sounds small until it reaches the seal, the filter or the joint. So far, we have treated the outside world as pressure and distance. Radiation has been part of it too. Now the outside becomes granular. Dust is easy to underestimate because on Earth it feels like dirt, cleaning annoyance. Off Earth, dust becomes a system hazard. It moves through interfaces. It rides on suits. It works into joints. It changes how machines age. Now think about a suit returning through an airlock. Dust on Earth can be brushed off casually. Dust on the Moon may cling electrostatically and ride into the habitat. Dust on Mars can arrive as part of the atmosphere itself. In both cases, the boundary between outside and inside becomes harder to defend than the word doorway suggests. Lunar dust is physically nasty. Without wind and water to round its particles the way Earth often does, lunar regolith can remain sharp and jagged. NASA has described it as clingy and abrasive. For suits and equipment, it was trouble. Apollo crews learned quickly that dust was not cosmetic. It entered cabins and irritated bodies. It wore surfaces. It challenged seals. Apollo gave us an early warning. Astronauts did not treat lunar dust as a minor nuisance after direct experience. It affected visibility in suits, equipment and cabins felt it too. Those short missions did not solve the problem. They revealed the beginning of it. A long-lived base would multiply every contact between dust and machinery. Now imagine that same dust on a base that depends on every seal working. The airlock is no longer a doorway, it is a contamination boundary. The suit joint is not merely a hinge, it is a life-critical moving part, exposed to tiny abrasive grains. The filter is not a maintenance convenience, it is part of the crew's lungs by extension. Mars gives a slower, broader version. Dust can settle everywhere because the planet has an atmosphere to move it. It can reduce solar energy and contaminate surfaces. Over time, it becomes a constant operational background. The base is not only sitting on dusty ground, it is living inside a dusty weather system. Mars dust is different. It is not the moon's vacuum dust. It is atmospheric dust on a planet with weather. It can cover solar panels and enter mechanisms. It can alter thermal behavior. In storms, it can last long enough to change power planning. It also carries chemical questions, including perchlorates, that matter for health and resource processing. So mitigation cannot be an afterthought. Airlock design and suit ports become part of livability. Cleaning systems and filtration do too. Surface stabilization, material choice, and maintenance routines follow from the same problem. The crew must treat cleanliness not as comfort but as mechanical survival. Here again the scoreboard fails. Lunar dust attacks the base at interfaces. Martian dust attacks the base as environment. One is sharp and static, cabin invasive. The other is planetary and persistent. It is tied to weather. Asking which is worse is less useful than asking how each dust couples into the failure chain. This is where the two worlds reveal different kinds of hostility. The moon is close but abrasive. Mars is more world-like but enveloping. The moon attacks through contact. Mars attacks through contact and atmosphere. Both force the base to defend its interfaces every day. On the moon, dust makes the nearby world less forgiving. The base may be close to Earth, but the surface will still grind hardware down. Suits need cleaning. Airlocks need discipline. Tools need design choices that assume abrasion from the start. A lunar settlement story that skips dust is not a settlement story. It is scenery, and interfaces are where systems fail. The line between outside and inside is not a single wall. It is every hatch and glove, every boot and bearing, every vent. Then come the filters and radiators. Even a cable pass-through becomes part of the boundary, every rover joint and sampling port. Dust turns that line into a maintenance campaign. On Mars, dust reaches deeper into the power and thermal system. If solar arrays lose output, the problem is not only electricity for lights, it is heat and air circulation. It is water processing and communication. It is medical capability. Sometimes it is the ability to make or store return resources. Dust becomes a way the planet touches every other system. We should be calm about this, not theatrical. Dust does not mean humans cannot live anywhere beyond Earth. It means living requires contamination control at a level ordinary life never teaches us. A house can get dusty. A habitat cannot casually get dusty if the dust is abrasive or chemically active. The deeper danger is dust able to undermine machinery, and this is one reason the moon has value as an early learning place, even though it is harsh. We can discover how equipment wears and how seals fail. Then we learn how cleaning systems behave on shorter loops. Mars needs many of those lessons too, but it has less room for the first version to be naive. Living off-world means the landscape is never just scenery. The ground becomes part of the machine, and the machine still has to hold the body in a gravity field we do not yet understand well enough. So resources change the mood of the comparison. They sound like independence, but every useful kilogram has to be found and extracted. Then it has to be cleaned and stored. Only after that can it be moved and protected before it becomes part of a living system. Dust is also a reminder that off-world environments do not need to be dramatic to be dangerous. The worst problems may be cumulative. A seal works slightly worse. A bearing wears slightly faster. A filter loads slightly earlier than expected. A rover joint needs more maintenance. A suit comes back dirtier than the protocol assumed. On the Moon, the danger is sharpened by the nature of the regolith and by the absence of weathering processes that make Earth dust familiar. Lunar dust can cling and scratch. It can darken surfaces. It can enter places designers wish it would not enter. Every repeated EVA becomes a negotiation with contamination. On Mars, dust is not only underfoot, it belongs to the atmosphere. It can move across regions and dim sunlight. It can cover hardware. Then it becomes part of the energy story. A solar-powered system on Mars is not merely a power system. It is a power system living under dust weather assumptions. These differences matter because they change what a base must prioritize. A lunar base may obsess over airlock discipline and suit ports. Abrasion-resistant materials matter. Keeping the cabin clean becomes a survival habit. A Mars base may obsess over solar margin and dust storm operations. It may also obsess over filtration, chemical contamination, and systems that breathe a dusty planet every day. Neither problem is glamorous, which is exactly why it belongs in the definition of live. A civilization is not built only from bold decisions. It is built from maintenance routines that keep small irritants from becoming system failures. So dust makes both worlds less like empty destinations and more like active engineering environments. The surface is not passive ground beneath the story. It is one of the story's main antagonists. Dust also affects how we imagine work outside the habitat. Every EVA is not just a walk. It is a contamination event and a suit wear event. It becomes an airlock cycle, a filter load, and a maintenance debt. The more routine outside work becomes, the more routine dust management must become. On the Moon, that may push designs towards suit ports and external suit storage. Robotic pre-cleaning, dirty zones, and outside-only tools may matter too. The architecture becomes a series of boundaries because one boundary is not enough. On Mars, the base may need a different rhythm. Weather forecasts and dust loading may shape the week. So may solar output, rover cleaning, and filtration. The crew may schedule work not just around human readiness, but around the planet's particulate behavior. So dust teaches a broad lesson. Living off Earth is not only about resisting the spectacular hazards, it is about surviving the ordinary environment without letting ordinary contact grind the system down. This is also where local experience matters. Dust behavior will surprise designers because no test chamber perfectly reproduces years of real use by tired crews with aging equipment. The Moon can send those surprises back to Earth quickly. Mars can teach the same lessons, but it will charge more for every mistake. So dust judges the boundary between outside and inside. A base that cannot control contamination is not merely untidy, it is losing its ability to stay sealed and filtered. Mobility suffers next. Repairability follows. The Moon and Mars challenge that boundary in different ways. Dust makes the outside cling to every return trip, so every doorway becomes an engineering argument. If dust is routine, then dust control has to become as routine as breathing checks. Gravity feels settled because Earth never lets us forget it is there. We notice gravity when it changes. On Earth, it is background. It shapes bones and muscles. It shapes blood flow, balance, and sleep. It may shape childhood development and the way the heart works over years. We do not experience it as a support system because it never takes a day off. Now partial gravity has a strange storytelling problem. It is less visible than dust and less immediate than pressure, but it may decide the difference between a rotating outpost and a place where human lives can unfold. Gravity acts slowly. That makes it easy to underweight and hard to forgive. Spaceflight has taught us a great deal about microgravity. Bodies lose muscle and bone without countermeasures. Fluids shift, vision can change, exercise becomes medicine. But the Moon and Mars are not microgravity. They sit in the unresolved middle between weightlessness and Earth. Let's say a crew can work for 6 months in lunar gravity with aggressive exercise. That would not prove children can grow there. Let's say a crew can live on Mars for 1 mission without catastrophic loss. That would not prove generations can thrive there. Settlement claims require much more than mission duration survival. The Moon gives about 1/6 of Earth's gravity. That makes movement strange, construction easier in some ways, and launching from the surface far less demanding than launching from Earth. But it does not tell us whether a human body can remain healthy there for years. Apollo visits were too short to answer that question. The Moon's low gravity may also help operations. Heavy equipment is easier to lift. Launch from the surface is easier. Construction may benefit from lower loads, but a civil engineering advantage is not a medical answer. A world can be easier for machines and harder for bodies at the same time. Mars gives about 0.38 GRE, roughly 3/8 of Earth's pull. It almost certainly has the stronger gravity argument. A body on Mars is loaded more than a body on the Moon. Movement may feel more stable. Fluids may behave less strangely. But likely better is not the same as proven enough. Mars's gravity feels like the more promising compromise. It gives the body more load while keeping launch energy far below Earth's. But we should resist turning a better number into a solved question. Human physiology did not evolve around 0.38 GRE. The threshold may not be a neat line, and different systems in the body may respond differently. Let's keep the uncertainty clean. We do not know the long-term human threshold for partial gravity. We do not know whether 1/6 GE is enough for healthy adult life with countermeasures. We do not know whether 0.38 GE is enough for childhood or pregnancy. We do not know what it means for injury recovery or old age. Those are not small details. They sit near the heart of the word settlement, so gravity creates a long experiment nobody has yet run. The Moon lets us run it sooner and closer. Mars may offer the better result if the number is high enough. Until the evidence exists, both claims must remain careful. This is where Mars gains a serious point without winning the documentary. If living means something more than temporary rotation, Mars's stronger gravity may matter enormously. It may make daily life, mobility and body maintenance easier. It may reduce the burden on exercise systems. It may give human physiology a better bargain. And this is one place where the word live changes most strongly with duration. A week can ignore questions a year cannot. A mission can tolerate medical debt a settlement cannot. Time makes gravity heavier, but the Moon answers with recoverability. If partial gravity causes problems, crews can return sooner. Medical data can be collected and acted on faster. Countermeasures can be changed on a tighter loop. The Moon may be the worst gravity environment, and still the better place to learn what partial gravity does. So gravity pushes in 2 directions. Mars may be better for the body. The Moon may be better for discovering how wrong we are. One advantage is biological. The other is operational. A grown-up answer has to hold both. And notice what gravity does to the 4 definitions. Engineered survivability can tolerate rotation and medical monitoring. Repeatable presence can tolerate uncertainty for a while. Failure-resilient settlement cannot. A true settlement cannot be built on a biological question nobody has answered. The body may decide what the machines cannot, but the machines still need power, and power is the hidden organ of every artificial world. And that is why psychology belongs inside the engineering question. The crew is not separate from the system. Human judgment is one of the systems that must keep working when help is far away. Gravity is where our confidence should be lowest and our caution highest. We have experience with Earth gravity. We have experience with microgravity in orbit. We do not yet have enough experience with human life over long durations in 1/6 Gi or 0.38 Gi to speak about settlement with certainty. That uncertainty matters because gravity is not only about walking, it is about the whole body over time. Bone remodeling and muscle loading may respond one way. Cardiovascular behavior, balance and immune changes may respond another. Sleep and injury recovery may follow one curve. Reproduction and development may follow another. A number that is good enough for one system may be insufficient for another. Mars probably has the stronger biological argument because 0.38 Gr is more than the Moon's 1/6 Gr. That could matter enormously. It may make daily life more stable. It may reduce the burden of exercise. It may make tools, fluids and movement behave in ways closer to human expectation, but probably is not proof. A settlement is not allowed to rely entirely on probably. Not when children and older people enter the picture. Pregnancies and decades of exposure make the question heavier. The Moon may be biologically worse and scientifically more reachable. Mars may be biologically better and operationally harder to study. This creates a useful sequencing argument. The Moon can help us learn what 1/6 G does and does not provide. Mars may eventually show whether 0.38 G is enough for deeper human life, but neither world can honestly claim full settlement readiness until partial gravity becomes a measured human fact rather than a hopeful inference. So gravity gives Mars a strong long-term point, while reminding us that every strong point still needs evidence. The partial gravity question also has a social dimension. If a place can support only highly trained adult crews for limited periods, it is an outpost. If it can support families and long careers, it begins to approach settlement. Recovery from illness and normal aging matter too. We do not yet know where the Moon and Mars fall on that deeper scale. This uncertainty should make the word settlement heavier. A lunar base may teach us whether 1/6 Gi can be tolerated with intense countermeasures. It may also reveal limits that force shorter rotations or artificial gravity strategies. Either outcome would be valuable because it would replace guesswork with evidence. Mars's 0.38 Gr may prove much more workable. If it does, Mars's long-term case strengthens dramatically. But we should not spend that evidence before we have it. Biology is not obligated to respect our preferred narrative. So gravity is not a minor footnote. It is one of the reasons early off-world living should be treated as an experiment in human physiology as much as an engineering achievement, so the gravity comparison should stay two-handed. Mars probably offers the better long-term biological environment. The Moon probably offers the better early research environment. If 1/6 Gi proves inadequate, that lesson matters. If 0.38 Gi proves adequate, that lesson matters even more, but both lessons require bodies, time, and careful measurement. So gravity remains an unanswered biological contract. Mars may offer the better bargain for bodies, while the Moon may offer the better place to discover the limits. A settlement claim needs evidence from time, not confidence from arithmetic alone. Gravity keeps the comparison humble because bodies will answer slowly, and slowly is exactly how settlements are judged. The body will not be persuaded by ambition, it will respond to load, time, and adaptation. A habitat without power does not slowly become uncomfortable. It stops being a habitat, so power deserves to be treated less like a utility and more like a life support organ. It is the condition that lets every other system pretend to be ordinary. Now the comparison becomes sharper. The Moon and Mars do not merely need electricity. They need electricity that can be repaired under local conditions. Tired people, limited spares, and abrasive dust are part of those conditions. Think of power as the organ behind all the other organs. Air circulation needs power. Carbon dioxide removal needs power. Pumps need power. So do the quiet systems in the background. Thermal control and communications depend on it. Medical equipment does too. So does the machinery that turns raw material into something usable. Electricity has to keep arriving. Now listen to the practical difference. On the Moon, a power fault is still dangerous, but the base can be designed around a shorter rescue and resupply loop. A failed component can become an urgent launch problem. A design flaw can be corrected on the next cargo flight. Earth can stay close enough to help interpret telemetry while the crew works the problem. But Mars asks for a thicker kind of independence. A failed inverter cannot be treated as a problem Earth will solve soon. Neither can a damaged array. A contaminated connector or dust-covered radiator has to be handled locally too. The base has to carry more diagnosis and more fabrication ability. It needs spare capacity. It also needs more judgment inside the local system from the first mission. So the power question is not simply solar or nuclear. It is repair culture. It is whether the crew can find the fault, prove the fix, and keep the habitat stable while the fix is still ugly. That is the part of livability people rarely put in the destination debate. Let's make that concrete. A livable power system is not the one that works on the best day. It is the one that leaves the crew options on the worst ordinary day. One option might be load shedding, another might be moving people into a smaller protected volume while repairs happen. A third might be swapping a module designed for gloved hands, in dust, under pressure, with the clock running. That kind of design sounds humble. It is actually the beginning of settlement logic. The machine has to expect imperfect maintenance, because people will eventually maintain it while tired and cold. They may be short of parts, while responsible for everyone asleep behind the hatch. Now power also decides where people can live on each world. A lunar polar site may be attractive because illumination can be better and volatiles may be nearby. But choosing a site for power may make access and construction harder. Communications, terrain and thermal control may get harder too. Every advantage enters a trade. On Earth, power failure is serious, but the atmosphere does not vanish. The walls do not stop holding pressure because the grid went down. Outside air remains outside air. Off Earth, power reaches into the boundary between life and environment. A base with weak power is not merely inefficient, it is closer to losing its artificial Earth. On Mars, the daily rhythm helps the human schedule. Crews can sleep and work under a cycle close to Earth's. That matters for psychology and operations, but solar arrays under a dusty sky are not equivalent to solar arrays in a clean Earth desert. The environment reaches directly into the energy budget. The Moon has a brutal timing problem. Away from special polar regions, the lunar day and night cycle can mean roughly 2 weeks of sunlight followed by roughly 2 weeks of darkness. That is not a normal night. It is a long storage and heating problem. It is also a survival problem that reshapes operations. Batteries and fuel cells become part of the conversation. Nuclear power and thermal storage enter the conversation. Careful siting does too. Let's name the dependency clearly. If power weakens, the base does not lose one service. It loses margin everywhere. Air chemistry becomes harder to control. Water loops become harder to run. Communications may be rationed. Thermal control narrows. Science, repair, and comfort give way to survival. The lunar poles may improve the story. Some high areas can receive more favorable illumination, and nearby permanently shadowed regions may hold valuable volatiles. But favorable is not magic. Power still has to be generated and distributed. Then it has to be repaired and protected in a place with dust, darkness, and difficult terrain. Nuclear power appears in planning because it offers steadier output through darkness and dust. But nuclear systems bring mass and complexity. They also bring heat rejection and safety cases. Launch politics and maintenance arrive with them. The word reliable does not mean simple. It means the whole risk stack may still be better than depending on sunlight alone. Mars has the kinder daily rhythm. A Martian sol is close to an Earth day, which helps operations and sleep. It helps the human sense of time too. But sunlight is weaker at Mars, and dust can reduce solar output. Regional or global dust storms can last long enough that human mission planning cannot treat solar power as a simple answer. The Moon can test these stacks close to Earth. Mars needs them to be stronger before arrival. That is the recurring asymmetry. The Moon lets human systems mature in a harsh nearby lab. Mars asks for more maturity because the support chain is thinner. NASA's Mars planning has therefore looked seriously at fission surface power for robust initial human missions. That does not mean every future base has one settled architecture. It means reliability matters more than elegance. The power system is not a preference, it is a survival premise. Power therefore becomes a definition test. A visit can ration energy and accept narrow margins. A base needs redundancy, a settlement needs power that remains repairable across years of component aging and human error, so the comparison again refuses a simple winner. The Moon has harsher light and darkness. Mars has friendlier day length but deeper weather and logistics problems. The Moon can be supplied and repaired on shorter loops. Mars needs more autonomy because a failed power component may have to be handled locally for a long time. Let's connect this back to living. A camping trip can ration power. A settlement cannot treat power as a bonus. The longer people stay, the more power becomes civilization. It means safe air and clean water. It means medicine and communication. It means workshop capacity and the ability to recover from mistakes. And if a base depends on making return propellant or critical consumables locally, power takes on another role. It is not only keeping people alive today, it may be preparing the way home tomorrow. A weak power system can therefore trap the mission inside its own assumptions. If power is fragile, the base is not a place, it is a countdown. And the next question is whether either world can provide enough local material to make that countdown less dependent on Earth. That is the operational discipline this question needs. A base is not proven when the first version works. It is proven when worn equipment can be understood, repaired and returned to service without turning every repair into a rescue request. So the power question lands on a simple rule. We cannot judge the Moon or Mars by the elegance of the generator alone. We judge each world by the whole repairable power culture around it, because the first dark hour after a fault is where livability starts to become real. Power also decides how ambitious the base can be. A minimal outpost can survive on tighter margins. A serious base needs workshops and medical equipment. It needs environmental control, communications and mobility. Science operations and resource processing come next. Each layer makes the base feel more like a place, and each layer increases the appetite for reliable energy. On the Moon, power planning is shaped by long darkness and extreme cold in shadowed regions. Polar illumination can help, but moving energy across rough terrain remains hard. A polar site may offer attractive sunlight and nearby volatiles, but it may also force hard choices about where people land and where they build. It may also decide how they route power to where resources actually are. On Mars, the day is kinder, but sunlight is weaker, and dust is part of the sky. Solar power may still be useful, but it has to be judged against storms and seasonal changes. Dust accumulation matters too. Cleaning and storage follow. So does the risk of long underperformance. Nuclear surface power appears in serious planning because it changes the base from a sunlight-dependent camp into something more robust. But nuclear systems are not magic boxes. They need heat rejection and deployment. They also need safety margins and protection. Maintenance assumptions and political acceptance have to be settled before they become ordinary infrastructure. So the comparison becomes practical again. The Moon can test power architectures close to Earth under brutal surface conditions with faster redesign. Mars needs a power architecture that arrives more ready to stand on its own. One world is better for learning reliability. The other demands reliability sooner. If power is the hidden organ of the base, then repairable power is the hidden organ of livability. Without it, every other system becomes a countdown. Power also decides the pace of ambition. With limited energy, a base becomes cautious. Fewer EVAs, less processing, less redundancy where people most want it. With abundant, reliable energy, the base can breathe more deeply. It can repair and experiment. It can produce. It can even waste a little without immediately risking survival. The Moon's long night makes stored energy and steady generation central. Mars's dust makes predictability central. Both worlds punish overconfidence, but they punish it differently. A lunar base may fail by underestimating darkness and thermal extremes. A Mars base may fail by underestimating atmospheric dust and seasonal variability. We should also avoid imagining power as a single plant. A livable base needs distribution and switching. Cables and connectors are only the visible layer. Batteries are visible too. Backups, fault isolation, and human procedures matter when conditions degrade. The generator is only the headline. The grid is the living system. So the serious question is not which world can receive a power unit. It is which world lets humans build a power culture that survives weather and darkness. Dust, wear, and the first mistake at 3 a.m. matter too. The power system also has to match the moral promise of the mission. If we send people to live, not merely visit, then power cannot be treated as a narrow engineering subsystem. It becomes the base's metabolism. A metabolism can run lean for a while, but a civilization cannot be built on permanent emergency mode. So power is not a supporting category. It is the condition that allows all other categories to keep acting like systems. The Moon stresses storage and darkness. Mars stresses dust and distance. In both cases, weak power turns a base into a narrowing margin. Power is the one margin that quietly becomes every other margin once the base is far from Earth. When power shrinks, choices shrink with it, and choice is one of the quiet forms of safety. The phrase resource is not supply should sit over every claim about living off Earth. So here is where we stand. We have moved from the body to the habitat, then to rescue distance, radiation and dust. Gravity and power followed. The question that remains is whether either world can stop being only a place we visit with imported equipment and become a place that contributes materially to its own survival. Now the industrial middle is where many settlement arguments become vague. They jump from ice to water supply, from CO2 to oxygen supply, from regolith to construction material. Each jump hides machinery. It also hides the maintenance burden of that machinery, which is exactly where living becomes hard. The tempting answer is to point at resources. The Moon may have water ice in permanently shadowed polar regions. Mars has a carbon dioxide atmosphere, accessible water ice in some regions, and a broader volatile story. These are real advantages, but a resource on a map is not a supply in a tank. A lunar ice operation would need prospecting that is precise enough to plan around. It would need excavation in extreme conditions. It would need thermal management and power. Processing and storage would follow. Quality control would follow after that. Then the system would need to keep working after dust and cold have had their say. Darkness and wear would have their say too. Let's slow down on that phrase. A resource becomes supply only after people or machines can locate it and access it. They have to extract and purify it. Then they have to move it. After that, they have to store and measure it, while repairing the system that does all of that. Every verb matters. If one step fails, the resource remains a scientific fact rather than a living system. A Mars oxygen plant has a clearer atmospheric feedstock, and MOXIE proved an important principle. But scale changes everything. A small experiment can demonstrate chemistry. A crew-critical plant must deliver quantity and reliability. Redundancy, monitoring, and repairability matter too. So does integration with storage and mission planning. The Moon's water ice could matter enormously. Water supports drinking and oxygen production. It can also support radiation shielding. In the right system, it becomes part of propellant chemistry. But lunar polar ice is not a lake with a pump beside it. It may sit in extreme cold and darkness. Concentration can vary. Excavation and power delivery have to work. Contamination control has to work too. Only then does processing become dependable supply. Let's keep that distinction clean. Demonstration is not deployment. Deployment is not dependable supply. Dependable supply is not settlement resilience. Each step is valuable. None should be skipped in the language. Lunar regolith also offers mass. Mass matters for shielding. It may matter for construction. But mass on the ground is not automatically an industry. Humans still need machinery that can dig and move. It must process and shape material. Then it has to inspect and repair under lunar conditions. The Moon gives material, not an easy factory. Mars may eventually benefit more from local resources because it has more to work with. But the first crews on Mars would also depend more painfully on those resources if mission plans require them for return or long-duration survival. Dependence turns an advantage into a vulnerability until reliability is proven. Mars has the stronger long-term resource canvas. Its atmosphere is mostly carbon dioxide, which gives oxygen production concepts a direct feedstock. MOXIE, carried by Perseverance, demonstrated oxygen production from Martian CO2 at small experimental scale. That is a real milestone. It is not a settlement-scale life support guarantee. The Moon can afford a more openly Earth-supported beginning. That may sound less visionary, but it is strategically powerful. Early operations can treat local resource use as learning and margin, rather than as the single point on which return depends. That lower consequence environment may be exactly where resource systems should grow up. And Mars's richer resource story comes with a harsher consequence story. If a lunar ice processing unit fails, Earth may still be close enough to send replacement hardware in a meaningful cycle. If a Mars oxygen or propellant system fails at the wrong time, the failure can reach into the return plan itself. The resource advantage becomes more valuable and more dangerous at the same time. This is the heart of the comparison. The Moon has weaker natural resources but a stronger external supply chain. Mars has stronger local possibilities but a weaker rescue and repair chain. One world leans on Earth, the other must replace more of Earth sooner. So the honest answer cannot be, the Moon has ice, therefore humans can live there. It cannot be, Mars has carbon dioxide, so oxygen is solved. Both statements skip the industrial middle. Living begins not when a resource exists, but when the system that turns it into supply can fail and recover. A place with resources is not yet a place with supplies. A place with supplies is not yet a settlement. And a settlement begins to become real only when maintenance becomes ordinary. So the final comparison cannot rest on beauty or distance. It has to rest on the ordinary day when nobody is landing, nobody is filming, and the base has to keep working because people are asleep inside it. The resource question is where optimism has to become industrial. A map can show ice, a spectrometer can detect useful chemistry, a rover can prove a process at small scale. None of those facts automatically feeds a crew. A supply is a resource that has passed through a working chain. It has been found where expected and accessed without destroying the equipment. It has been processed to the required purity, stored safely and moved to use. Then it has to be measured reliably and produced again after maintenance. That is a much higher bar than existence. The Moon's possible polar water ice is valuable because water is versatile. It can support life and radiation shielding. It can also support oxygen production. In the right system, it opens propellant pathways, but extracting ice from permanently shadowed or extremely cold terrain may be one of the hardest industrial tasks humans have attempted off Earth. The advantage is real, but it is not effortless. Mars offers a broader resource story. A carbon dioxide atmosphere gives a direct feedstock for oxygen production, and MOXIE showed that this chemistry can work in principle on Mars. Subsurface or regional water ice could matter for life support and fuel. The planet gives more raw material to imagine with. But Mars also makes dependence more consequential. If a Mars mission relies on local oxygen or propellant and the system underperforms, the problem reaches into return and safety. Mission duration changes too. A lunar resource experiment can fail and still teach. A Mars resource dependency can fail and trap assumptions. So resources strengthen Mars's long-term case and strengthen the Moon's early learning case at the same time. Mars may have more to work with. The Moon may be the safer place to learn how work becomes supply. The difference between resource and supply also changes the business case of each world. If local materials can reliably replace imported mass, the cost structure of living changes. If they cannot, the base remains tied to launch windows and budgets. Earth-side manufacturing remains in the chain. That economic reality is part of livability, because a base that is technically possible but endlessly unaffordable may never become repeatable. The Moon's weaker resource canvas might still be enough for valuable early uses. Shielding mass is one. Construction experiments are another. Oxygen extraction research and targeted water processing could follow if the ice proves accessible. Those are not small gains. They are steps toward reducing dependence. Mars's richer canvas may eventually support a broader industrial loop, especially if water and atmospheric processing can be made robust. But the more a mission depends on local production, the more every production system becomes life-critical infrastructure. So we should value resources without worshipping them. They are invitations to build industry, not industry itself. The worlds do not hand supplies to humans. Humans have to earn supplies by making machines that can keep working where normal factories do not exist. This also separates exploration from industry. Exploration can celebrate detection. Industry has to deliver repeatability. A rover finding ice is important. A plant producing clean water every week after seals wear and filters clog is a different achievement. Living requires the second kind of achievement. So resources become meaningful only when they become boring. Ice and carbon dioxide matter most when crews can depend on the conversion chain. Regolith matters in the same way without treating every production cycle as an experiment. Until then, resources are promise, not life. Resources matter most when they stop being discoveries and become scheduled output the crew can trust. A resource claim becomes serious only when maintenance is included in the production story. Arrival is cinematic. Maintenance is civilization. The first landing will always take the picture, the first footprint, the first hatch opening, the first habitat lights glowing against alien ground. Those are the moments people remember. But none of them answers whether humans can live there. Living begins on the day after the celebration, when something ordinary breaks. Now maintenance also changes the kind of people a base needs. Exploration crews can be selected for science and operations. Piloting and medicine round out the mission. Engineering does too. A settlement-like base needs repair generalists and inventory discipline. It needs tool culture and training pipelines. It also needs the humility to design for work done tired. A base ages from the first hour. Seals flex, filters collect particles, radiators lose efficiency. After that, the pattern spreads, bearings wear, software behaves strangely, batteries degrade, suits collect damage, tools go missing, and spare parts get used. The base does not fail once in a clean dramatic event. It becomes a long argument against entropy. The romance of self-sufficiency often skips the warehouse, but a base lives or dies through what it has stored and labeled. It also depends on what has been protected, tested, and made interchangeable. A spare part is not useful if nobody can find it or install it. It still has to be verified. And if the original failure was misdiagnosed, the crew may need to adapt it. On the Moon, maintenance will be hard. Dust and vacuum will punish equipment. Radiation and thermal cycling will do the same. Weak gravity adds its own uncertainty. But the Moon allows a maintenance culture to grow with Earth close behind it. A bad component can be redesigned. A procedure can be changed. A tool can be sent. A crew can come home sooner if the risk grows faster than expected. On the Moon, teleoperation and Earth-based expertise can help shape that maintenance culture. Engineers can inspect data and update procedures. Revised tools can follow with relatively quick feedback. The lunar base can become a joint organism, crew on the surface and support on Earth. Machines sit between them. Mars asks for a more mature maintenance culture from the beginning. The crew cannot assume the next cargo flight will arrive on a convenient schedule. The workshop matters more. Cannibalizing parts may become part of survival logic. Local manufacturing and diagnostics move toward the center of life. Software patches, medical improvisation, and disciplined inventory move there too. Mars needs more of that organism to fit inside the mission. The crew cannot wait for a live troubleshooting conversation in the same way. They need onboard knowledge systems, perhaps AI assistance, but also practical authority. The person standing beside the broken machine may become the final decision maker sooner. Here's the difference in one spare part. On the Moon, a missing spare is a serious problem inside a shorter loop. On Mars, a missing spare can become a mission architecture problem. The same piece of hardware carries different moral weight because the distance changes how much improvisation must happen before help arrives. So maintenance is also governance. Who decides when to repair and when to cannibalize? Who decides when to risk an EVA, reduce operations, or prepare for evacuation? The farther the base is, the more those decisions move from Earth to the crew. This is also where systems couple together. A power failure can affect air. An air failure can affect crew performance. Dust can affect seals, which affect pressure, which affects safety margins. A medical problem can reduce the number of people available to repair the power system. Nothing lives alone inside a base, and that is a settlement-shaped problem. A place becomes livable not when nothing breaks, but when breaking becomes part of normal life. The Moon is closer to letting us learn that. Mars is closer to testing whether we have really learned it. So maintenance is not a support function. It is the definition of repeatable presence. A base that works only when everything is new is not a place people can live. It is a demonstration. A base that keeps working after the first wave of failures teaches us something deeper. The Moon's strongest case is that it lets those lessons arrive sooner and less finally. We can build imperfect systems, learn from their damage and improve them, while Earth remains close enough to keep the experiment from becoming a one-way test. That is not glamorous, but it may be how livability is earned. Mars's strongest case is that the same maintenance culture once achieved there would mean something larger. A Mars base able to repair itself through dust and delay would already be impressive. Add distance and resource uncertainty, and the claim becomes much stronger. But the price of reaching that claim is higher. Living begins when the first version breaks and the second version still works. And after the machines, we still have to ask about the people inside them. That is the operational discipline this question needs. Every system has to be judged not only by whether it can work, but by how it fails and who can repair it. Then we ask how much time the crew has before one broken part becomes several broken assumptions. Now the maintenance question brings the comparison back to its center. We are not asking which world can host the cleanest first module. We are asking which world allows a dirty, aging, imperfect base to keep becoming usable after the original plan meets the surface. So we keep coming back to the same unforgiving measure. We do not ask whether the first base can look alive on landing day. We ask whether it can still be made livable after wear and dust. Tired people and imperfect parts arrive next, have done ordinary damage. Maintenance is where settlement language either becomes serious or collapses. A mission can be designed around replacement. A settlement has to be designed around repair and reuse. Improvisation and documentation matter. Local competence matters just as much. The farther the base is from Earth, the more maintenance becomes culture rather than procedure. This means the workshop may be as important as the habitat. A base needs tools that can fix the tools. It needs spare parts chosen not only for likelihood of failure but for consequence. It needs common fasteners and accessible panels. Inspectable seals, clear inventories and adaptable parts matter when the exact replacement is gone. On the Moon, Earth can help build that culture. Engineers can study returned components, crews can rotate through lessons. Design teams can push improvements into the next mission on shorter cycles. The Moon gives us a place where maintenance knowledge can mature without every mistake being separated from rescue by interplanetary distance. Mars requires a more closed maintenance world. The crew needs the ability to diagnose without live conversation and repair without new shipments. It also has to decide without waiting for Earth to carry responsibility. That is closer to settlement behavior, but it is a harsh place to learn it for the first time. So if the Moon is a school of failure, maintenance is its main subject. The lesson is not simply how to build the first base. The lesson is how to keep a base from becoming less livable every day after it opens. Mars will need the same lesson, but with fewer excuses. That is why it belongs later in the ladder. Maintenance also forces humility into design. Engineers can design for nominal operation, but crews live in off-nominal reality. A latch sticks, a connector corrodes or abrades. A diagnostic gives conflicting readings. A repair that was simple on Earth becomes clumsy in gloves. A part that was supposed to last 5 years lasts 2. On the Moon, this becomes a feedback engine. Returned parts can be examined with full Earth laboratories. Astronaut reports can shape the next hardware generation. Robotic systems can be tested alongside human systems. The base becomes a long-running experiment in how machines age beyond Earth. On Mars, the same aging may have to be understood in place. The crew may not be able to return failed parts for analysis. They may need to document and inspect. Then they have to repair and adapt while still using the system. That is a higher bar for both people and design. So maintenance is the bridge between survival and settlement. Survival asks whether the machine works today. Settlement asks whether the people can keep making it work after today stops being special. That is why elegance can become dangerous if it makes repair harder. A beautiful sealed unit may be perfect on Earth and hostile on the Moon or Mars if it cannot be opened and inspected. It also has to be cleaned or patched by the crew. Off-world design has to respect the person who will meet the failure later. So maintenance turns ambition into a daily discipline. The test is not the clean first habitat photograph. The test is whether the crew can keep the habitat becoming habitable again after wear and dust accumulate. Fatigue and imperfect repairs accumulate too. Maintenance is the proof that the base is learning faster than the surface is wearing it down. Maintenance is where engineering stops being launch hardware and becomes daily life. The farther world does not only demand stronger machines, it changes the mind living beside them, so rescue distance becomes psychological before it becomes physical. A crew does not have to panic for distance to matter. It only has to know calmly and continuously what kind of help can no longer arrive. We should keep this calm. The psychology of Moon and Mars is not a horror story. It is an operational fact. People make decisions differently when rescue is imaginable than when rescue is abstract. Crews can be brave and trained. They can be cohesive and still be affected by distance, delay, and confinement. Workload and medical uncertainty add their own pressure. Now imagine two crews hearing the same alarm. The lunar crew knows Earth is close in the sky and close in the radio loop. It is also close enough that a rescue or replacement mission belongs to the realm of planning. It may still be too late for a specific crisis, but psychologically, help remains concrete. Mars changes that background assumption. The crew can still be supported. They can still receive expertise and procedures. Medical advice and emotional contact still arrive. But the support arrives through delay and cannot become hands-on. The difference is not courage. It is the kind of burden the crew has to carry every day before anything goes wrong. So the psychology of rescue becomes part of the habitat. It shapes sleep and risk tolerance. It shapes maintenance discipline, medical decisions, and the way people talk about small symptoms. A base that is technically survivable but mentally brittle has not solved the problem of living. Now the psychological difference also begins before arrival. A Mars crew knows the journey itself commits them to distance. The Moon is a nearby world with a hard surface. Mars is a campaign of time. That difference affects how risk is imagined, how families prepare, and how crews understand the meaning of an emergency. On the Moon, isolation is real. The landscape outside is airless. The habitat is small. The crew is dependent on machinery, but Earth is visible in the sky from many locations. Communication can be close to real time. Family contact and medical consultation. Mission support remain emotionally and operationally nearer than they would be on Mars. Communication delay does not only slow instructions, it changes relationships. A conversation with family becomes asynchronous. A medical consultation becomes staged. A disagreement with mission control cannot be resolved with the same real-time texture. The crew must carry more emotional and operational closure within itself. That does not make the Moon easy. A medical evacuation from the lunar surface could still be difficult, risky, and slow compared with any hospital on Earth. But it remains imaginable on a human timescale. That matters. Risk tolerance changes when the crew knows that the emergency system still includes home in a practical way. On the Moon, Earth can still be a visible reference point. That does not erase confinement and stress, fatigue, or danger, but visible Earth and fast communication may help preserve a sense that the crew remains near the human world rather than separated into a fully independent outpost. Mars is different. Earth becomes a delayed voice from another planet. A message can take minutes to arrive and minutes to return. During some moments, that may be manageable. During an emergency, it changes the nature of help. Mission control can support, but the crew must act through the first version of the problem themselves. Mars may require a more ship-like psychology. The crew is not merely stationed somewhere, it is the local society for a long period. Trust becomes infrastructure. Conflict management becomes safety equipment. Sleep and privacy, workload and mission meaning all become part of the life support system in the broad human sense. NASA treats isolation and confinement as human spaceflight hazards. Distance from Earth and hostile closed environments, radiation and altered gravity belong in the same risk family. These are not separate checkboxes inside a Mars mission. They stack. Fatigue can make maintenance worse. Communication delay can make medical decisions harder. Confinement can amplify conflict at the exact moment cooperation matters most. Medical autonomy sharpens the point. On Mars, a doctor may be present, but the hospital is not. Supplies are finite. Specialist advice is delayed. Procedures must be planned for conditions where evacuation is not the default answer. That changes what kinds of illness and injury are acceptable mission risks. Let's connect psychology to the word live. A temporary crew can accept a level of isolation as part of a mission. A settlement claim requires something more stable. People need routines and repair cultures. They need authority structures and medical competence. Privacy, trust, and a believable path through ordinary bad days matter too. Livability includes the human system, not only the hardware. So psychology does not crown the moon forever. It says the moon is the nearer human experiment. Mars is the deeper isolation experiment. Both matter, but confusing them leads to shallow confidence. The moon's closeness may soften that system. Crews can rotate more easily. Earth can provide live expertise. Families and specialists can remain part of daily support. The emotional fact of Earth in the sky may not solve loneliness, but it changes the meaning of being away. Mars asks people to live with a different kind of uncertainty. The crew may know Earth hears them. They may also know Earth cannot arrive in time. That gap between being heard and being helped is one of the quietest differences between the two worlds. Again, Mars's hardship is not an argument against Mars forever. It is an argument against careless language. A Mars settlement would represent a deeper human step precisely because the psychological and operational distance is so large. But calling that livable before the system proves itself would be borrowing confidence from the future. The farther world requires humans to live with a longer failure chain inside their heads. And now we can return to the original question with the definitions separated. And we should hear the humility in that. The evidence is strong enough to reject the easy story, but not strong enough to pretend every later question is solved. Good science does not make the frontier disappear. It tells us where the frontier really begins. The psychology question also changes the definition of success. A crew can endure hardship for a mission when the endpoint is clear, the support system is strong, and the meaning of the sacrifice is shared. Living asks for more than endurance. It asks whether daily life can remain stable and competent. It has to remain humane inside a closed system under constant technical dependency. On the moon, Earth remains psychologically present in a way that matters. The delay is short. The planet may be visible. Families and doctors can stay closer to daily experience. Engineers and mission control can stay closer too. That does not remove stress, but it changes the emotional geometry of danger. Mars creates a more separate human environment. Communication becomes delayed. Private grief and conflict occur inside a small group that cannot easily leave. Boredom, fatigue, and fear do too. The crew must become its own first responder emotionally as well as technically. This matters because human performance is part of the machine. A tired crew misses details. A divided crew repairs worse. A medically stressed crew has less margin for a power problem. A psychologically overloaded crew can turn a manageable failure into a cascading one. So livability includes trust and privacy. Leadership and schedule design matter. Medical confidence and a believable future matter too. Those are not soft extras. They are operational systems carried inside people. The moon gives us a nearer place to learn that human system. Mars asks whether the human system can remain strong when Earth is supportive but no longer near enough to rescue quickly. There is another psychological difference, the meaning of choice. On a lunar base, a crew may know that leaving is difficult but imaginable. On Mars, leaving is tied to planetary windows and return systems. Health and fuel shape the decision. Mission architecture decides the rest. The option to leave becomes less like a door and more like a campaign. That changes how people experience conflict and uncertainty. A minor disagreement in a normal workplace can be softened by distance, privacy, or outside relationships. In a small Mars habitat, the social world is narrow and the stakes are high. The crew's culture must prevent small fractures from becoming operational hazards. We should not assume this is impossible. Humans have endured ships and polar winters, submarines and space stations, but Mars combines confinement with distance and delay, partial gravity and radiation. Extreme dependence on machinery add to the load. The stack matters, so the human system has to be designed as carefully as the air system. Training and selection matter. Governance and rest matter. Ritual, conflict management, and meaningful work decide whether people can live there rather than merely endure. The psychological comparison also affects families and institutions back on Earth. A Moon crew can remain part of a fast support culture. A Mars crew becomes a more separate human unit for longer. The public story may focus on distance traveled, but the crew lives inside distance experienced, so psychology belongs inside the engineering answer. A crew under delay and confinement is not separate from the machine. It is part of how the machine is operated and interpreted. It has to be repaired and trusted. Mars makes that human system carry more weight. The human system matters because the best procedure still has to pass through tired people under pressure. A crew that can stay calm, coordinated, and honest under stress is part of the survival architecture. The honest answer is not a planet name. It is what the word live is being asked to carry. We began with a familiar choice: Moon or Mars, close or planet-like, grey world or red world. Now the question has changed shape. We are no longer asking which destination sounds more like home. We are asking which definition of living each world can support. Now we can see why the answer should resist a dramatic winner. A winner implies one world solves the question. Neither does. Each world exposes a different meaning of live and a different weakness in our assumptions. If living means natural habitability, the answer is neither. The Moon gives no breathable atmosphere and no ordinary pressure. Mars gives a sky but not air a human can breathe, or pressure a human body can use. Both worlds require a sealed boundary before life can begin. The Moon is not humanity's second Earth. It is a nearby place where the absence of Earth becomes manageable enough to study. Its gift is not comfort, its gift is iteration. It lets humans find out what breaks when a base tries to behave like a small planet. If living means engineered survivability, the Moon has the first practical edge. Not because it is gentle, it is not. The Moon is harsh and dusty, it is irradiated and thermally difficult. But engineered systems fail, and when they fail near the Moon, Earth can still matter on operational timescales. Advice and spares stay closer. Redesign and evacuation stay closer. Repeated learning stays closer too. Mars is not humanity's ready-made home. It is a world with stronger long-term ingredients and a longer failure chain. Its promise is larger because it asks for more genuine local capability. Its danger is larger for the same reason. If living means repeatable human presence, the Moon likely comes first again. A lunar base can be Earth-supported without pretending to be independent. It can be a place where crews learn how habitats age and dust invades. They can learn how shielding works and how partial gravity affects bodies. They can learn how maintenance cultures form beyond Earth. If we are precise, the answer becomes useful. The Moon first for recoverable engineered presence. Mars stronger for long-term planetary potential. Neither yet for failure-resilient settlement. That is not hedging, it is the answer the evidence supports. That if living means the richer long-term planetary canvas, Mars has the stronger case. Mars has more gravity and a more useful day length. It has a thin atmosphere and carbon dioxide for processing. Broader resource possibilities sit behind that. It feels less like a worksite and more like a world that could one day host a deeper human project, and it gives us a better way to hear future claims. When someone says humans will live on the moon or Mars, we can ask, live how? For how long? With what supply chain? With what repair capacity? With what medical escape? With what tolerance for ordinary failure? The cost is that Mars asks for autonomy earlier. The base must absorb more failures locally. The crew must tolerate longer delays. Resource systems must work with higher consequences. Maintenance must be more complete. Medical and psychological independence must be stronger. Mars may be the better long-term canvas and the harder first place to fail safely. Those questions do not make the dream smaller. They make it real enough to test. A dream that cannot survive definitions cannot survive a broken air pump. So the common answer, Moon first and Mars later, is partly right, but too thin. The real sequence is not a slogan, it is a ladder of definitions. First survive in machines, then repeat presence, then learn repair. After that, turn resources into supply. Only then can we see whether any place beyond Earth can keep human life going after the easy support assumptions break. Under that ladder, the Moon is the nearer school of failure. Mars is the larger exam. Neither is a natural home. Neither has proved settlement resilience. Both are less a destination than a test of whether humans can carry enough of Earth with them, and then slowly learn which parts can be replaced, and the most important reversal stays with us. The first off-world place humans can live may not be the place that looks most Earth-like. It may be the place where mistakes can be survived long enough to become knowledge. That is the adult answer to the Moon or Mars question. The Moon has the edge for early recoverable human presence. Mars has the stronger long-term planetary promise. Neither has yet earned the full meaning of live. So the useful comparison keeps moving away from romance and toward recoverability. We are not draining the wonder from the Moon or Mars. We are protecting the wonder from bad accounting. A world beyond Earth becomes more interesting, not less, when we ask what it costs to keep people alive there after the first triumphant image fades. So the final answer has to stay layered. We should not flatten it into a slogan just because slogans are easier to remember. The Moon answers one definition of living first. Mars answers another more strongly later. The full word still waits beyond both. The definition ladder gives us a cleaner way to hear every future claim about human settlement. When a headline says humans could live on the Moon, we can ask which definition it means. A crude outpost? A rotating research base? A semi-permanent industrial site? A community that can handle failures locally? Each version carries a different burden. When a headline says humans could live on Mars, we can ask the same thing. Does it mean the first mission survives? Does it mean oxygen can be made experimentally? Does it mean a base can be resupplied every launch window? Or does it mean people can remain there even when a critical machine breaks and Earth cannot send an answer in time? That is why the answer is layered rather than evasive. The Moon wins the early recoverability test. Mars wins more of the long-term planetary potential test. Neither wins the natural habitability test. Neither has yet won the failure-resilient settlement test. And this layered answer is more useful than a simple winner. A simple winner invites the wrong next step. If the Moon wins, people may underestimate how hard the Moon is. If Mars wins, people may underestimate how much autonomy Mars demands. The definition answer keeps both ambitions honest, so the grown-up view is not anti-Moon or anti-Mars. It is pro-sequence. Learn close where mistakes can be recovered. Test deeper autonomy when the systems have earned it. Keep the romance, but make it answer to maintenance and power, health and time. That is how a destination becomes more than a destination. It becomes a proof that human life can carry a small part of Earth into a place that never promised to welcome it. This answer also explains why future programs should not be judged by a single heroic milestone. A lunar base that depends heavily on Earth can still be a success if its purpose is to learn recoverable off-world living. A Mars mission that remains small and dependent on prepositioned supplies can still be a success if it proves key autonomy pieces. The danger is pretending either has solved more than it has. The better public language would be staged. First, human-tended outposts. Then repeatable bases. Partial local supply comes after that. Repairable local systems are the deeper test. Then, much later, communities that can absorb failure without immediate Earth rescue. Each stage deserves its own evidence. Under that staging, the Moon is not merely practice for Mars. It is where humans may discover whether the basic disciplines of off-world life can become routine at all. Mars is not merely the next trophy, it is where those disciplines face the deeper test of distance, so the final view is firm. The Moon is the nearer answer for living as recoverable engineered presence. Mars is the stronger answer for living as a long-term planetary ambition. The full settlement answer remains unearned, and that honesty is what makes the question worth asking. So the answer should leave the viewer with a tool, not just a conclusion. When future claims arrive, ask which definition is being proven. Natural home or engineered survival, repeatable base or resilient settlement. Most announcements will prove only one rung. The mistake is pretending one rung is the whole ladder. So the final definition has to keep its layers. The Moon answers the early recovery question better. Mars answers the long-term planetary potential question more strongly. The full settlement question remains open because neither world has yet proved ordinary failure can be absorbed. The ladder matters because it lets us respect both worlds without pretending either has already become a home. That is the lasting answer. Different worlds, different definitions, and no shortcut around proof. So the conclusion should feel useful rather than tidy. If a viewer leaves able to ask better questions about any future Moon or Mars claim, the comparison has done its job. Which definition is being used? What failure chain is being shortened? What resource has actually become supply? What support still comes from Earth? Those questions turn a familiar space debate into a practical map of the work still ahead. That practical map is the real payoff. Not a slogan, a way to judge every future promise with sharper, calmer, reality-tested eyes. So where could humans actually live? The Moon or Mars? The honest answer is that the question only becomes clear after the word live has been made smaller, sharper, and more honest. If live means standing outside as a human body, then neither world qualifies. The Moon gives no air and no pressure. It gives no natural shelter. Mars gives a sky and a day that feel familiar, but not a world the body can use. Both places begin by refusing biology. If live means surviving inside a machine, then both become possible in principle. But the Moon has the first practical edge. Not because it is kinder, because it is closer to correction. Earth can still advise. Earth can still send. Earth can still receive a crew back before every failure becomes a planetary commitment. If live means repeatable presence, the Moon still has the nearer path. It is the place where humans can learn how off-world systems age and dust enters. They can learn how partial gravity changes bodies and how power margins shrink. They can learn how maintenance becomes ordinary. It is not home. It is the first place where the hard lessons can arrive close enough to be used. Mars carries a different promise. Mars has more of the ingredients that make a world feel like a world. Its day is close to ours. It has more gravity, an atmosphere to process, and a surface that can hold a larger long-term imagination. But Mars also stretches every failure chain. Help is delayed. Supplies are seasonal. Medical choices become heavier. Repair has to happen farther from the people who designed the system. So the answer is not Moon wins or Mars wins. The Moon is the stronger candidate for the first recoverable human base. Mars is the stronger candidate for a deeper long-term planetary project, and neither world has yet earned the full claim of a failure-resilient settlement. That is the promise from the opening paid off. The most livable place is not automatically the most Earth-like place. It may be the place where mistakes can be survived long enough to become knowledge, and that changes how we should hear the whole future of human spaceflight. The question is not whether humans are brave enough to go. We already know that. The question is whether the systems we build can fail in ordinary ways and still leave people alive, capable and learning. A habitat wall is not just a wall, it is the atmosphere. A power cable is not just a cable, it is heat and air. It is water, communication and time. A spare part is not just hardware, it is the difference between a mission that endures and a mission that waits for rescue. The same question appears in the next step of this lane. Why going back to the Moon is still so hard, even when the Moon is the closer world. That is the natural end screen path, GNS Space 016, because closeness solves less than we wish and more than we should ignore. For now, the adult answer to Moon or Mars is a definition. The Moon first, if we mean recoverable engineered living, Mars later, if we mean the larger planetary canvas. Neither yet, if we mean a place where human life can keep going after the machines start failing. And that is the real frontier, not arrival, but recovery. Not the first footprint, but the first ordinary failure that does not end the story.